around a little bit. Ignore my very messy desktop. I get a lot of comments on that. And then I think I kind of want to do this for y'all. Just shuffle around. Philip is not done.
Probably conference.
Okay. And then just share all of this on Zoom as well. All right, friends on Zoom, if it's not working and you can't see the slides, then please let me know. I think I managed to share in presenter view, so you're seeing the slides on the screen. That's beautiful. Thank you, Bethany. I loved it. Love the support. Fantastic. All right. Okay. Yes. Welcome to COMCEPTS, which is a wonderfully not at all forced acronym for Combined Ocean Mixing Course Experiments and Practices for Turbulence Sampling. Ta-da! And we're on day 1, and this is the first lecture, and I titled this, AKA, What Are We Even Doing Here? And you've seen this pretty little logo that we have there too, that's on your sticker. And I designed that hoping to try to tie in a couple of elements from what you'll take away from this course. Okay, the outline for this lecture, what I hope that you guys take away, is that we're going to talk a little bit about why we even care about measuring turbulence and mixing. I'm going to give a few brief touch points on the history of turbulence theory and turbulence sampling. And then we're just going to review a few concepts, just so we all feel like we're on the same page again. Diffusion, stirring, mixing, turbulence, some of the Navier-Stokes equations in case you haven't done that recently, and then a couple of common force balances and non-dimensional numbers. In the student drive, there is these slides as a PDF that you're welcome to take notes on. And there's also a complete set of lecture notes that has all of the math on it, because this is a review lecture. I am doing the terrible faux pas of doing a bunch of math on slides. I apologize. But yes, they're all in the lecture notes. So if you don't feel like writing them down, they're there and you can look at them at your leisure. Okay, why measure ocean turbulence? Rhetorical questions, answers from the crowd. Any thoughts? Dead silence. Why are you all here?
Because we are interested in how the ocean moves.
Yeah.
And the energy drives.
Energy, I like that word. Movement, yeah. Anything else?
Ocean mixing.
Ocean mixing, yeah. Ties into the energy, the motion, yeah. Where things are flowing and why. Anything else? You're all just here because oh yeah, we get to go to sea and mixing sounds cool, this is sweet. All right, I'm gonna stop harassing you. I know it's early in the morning. I'll just pick on to the next slide. Ocean turbulence matters for a lot of things in the ocean. It's how I heard the word energy, it's how we close the energy budget in the ocean, right? Which means that it is of importance for things such as, understanding global overturning and circulation. That is what we need to make good climate models. We think about salt, heat, momentum, where that goes, where it goes, energy transfers across scales, waves, diapycnol, so across pycnol, fluxes, water mass transformation. And then there's this whole other thing, all of the organisms that live in the water that gets moved around too. Carbon cycles, nutrient cycles, and ecosystems, from coral reefs to planktons to a bunch of different things that also care about how the ocean moves and the mixing that is going on. So I don't know if you've heard of the GCOS, the Global Climate Observing System. This is an effort by the UN Environment, International Science Council, a bunch of other WMO, where they have listed what's called EOVs, essential climate variables, and then they also have a set of essential ocean variables. So the climate variables, there are a couple of terrestrial ones, the water cycle on land, the biosphere, the anthroposphere, humans, atmosphere, cryosphere, etc. And then they have a bunch of the ocean variables. And there has recently, or I should say these variables are all addressed based on impact, as in whether or not the variable addresses climate, operational ocean services, and ocean health, and contributes to understanding from a scientific perspective or application from a service perspective. So that's one of the criteria for whether or not a variable is essential. And then there's also a feasibility criteria. So that is it technically, politically, or economically feasible to observe or derive the variable on a global scale using proven scientifically understood methods. And there's recently a push to turn turbulent diapicnial fluxes into one of these essential ocean variables. This was a push actually by some of the people in our lab. So Arnaud and Nicole and Matthew are all people that you're going to get to meet during this course and learn from. But yeah, turbulence is today considered an essential ocean variable. It's one of those things that we need to understand and measure, which is pretty cool. Justifies why we're here. Okay, how long have scientists been thinking about turbulence? Can I get a guess? Any this is past decade or past, I don't know.
18th century?
18th century, yeah, you're not too far off. One of the first people who actually talked about turbulence was this guy. I'm a hobby philosophist. I'm an armchair philosopher, you could say. I love philosophy and I love quotes. Kant is someone you might have heard of, not in the context of turbulence, but now you have. This man said unforgivable quotes such as, "Rules for happiness, something to do, someone to love, and something to hope for." That's sweet. He said, "Out of the crooked timber of humanity, no straight thing was ever made." Think of that what you will. And then he said, "Science is organized knowledge, and wisdom is organized life." I'll let you suck on that one for a second and just take that in. But yeah, Kant was also wrote a bunch of moral and philosophy and whatnot, but as a lot of white men back then, he had a bunch of ideas on science, and because he knew how to read and write and stuff, and he could just write those down, and people would be like, "Oh, this is probably a good thought." And he was one of the first to point out that maybe there's something to do with friction from the tides, that can help explain why the motions of the ocean, of the moon and the sun are sort of slightly misaligned. So it was one of those first recorded notions of oh yeah, maybe there's something to do with friction, turbulence, swarthiness kind of thing that can help explain better how our planet, solar system sort of level moves. Then a couple of years later, there was, or actually I have to say a decade later almost, there was this push by the British government called the HMS Challenger expedition. Sorry, I should say too that this, in the lecture notes, you'll find a lot more. I have I've done a non-comprehensive and very arbitrary list of touch points in history, and I'm taking a selection of those on the slides, but the full list that I made is in the lecture notes. But yeah, late 18th century, the British government sent a ship on an expedition around the world. It took them 4 years. They collected about 4,700 new species. They took pictures of icebergs for the first time. They took out a bunch of their guns and put in scientific instruments instead, and that's a very lovely sentiment, I think. But one of the things they did too was that they took a bunch of temperature samples. And one of the things they concluded is that the deepest water we see in the ocean seems to only be forming at high latitudes, right? They went down to the Arctic, kind of, and fairly high up as well in the Atlantic. And they concluded that, there's something here in the circulation level that we see turbulence. And this expedition is, we're going to come back to that in a second. And around the same time, Osborne Reynolds published a very famous paper where he discusses laminar and turbulent flows. And we'll come back to this in a couple of lectures. Helen will talk more about this. This is a figure from the paper itself. Scientist in his three-piece suit. It's very sweet. And very detailed drawings of all of the equipment. But yeah, this is also one of those like kind of seminal touch points in history. Give it another couple of decades, and then we have another set of observations coming from a Swedish guy named Ekman. Here's the same of the Ekman-Ekman flux that you've probably should ring a bell somewhere in the back of your mind. This idea like how does water move under wind forcing? He was in a boat called the Fram and went sailing up around icebergs and was like, the boat is moving, should be moving a lot faster than what we are moving with the sails and everything gathered up, but we're sort of slowed down. And they call this thing dead water. It's actually internal waves, which is something that we'll come back to later in this course as well. First documented observation of internal waves. And then I would be remiss if I didn't mention the 1966 paper by Walter Munk. Munk was a Scripps professor for many, many years. He died almost a decade ago at this point. Munk mentions the Challenger expedition and says, well, there's something about this upwelling idea that deep water forms in certain places. Where does it go? How do we sort of square these observations we have from across the world where we have these deep profiles of temperature and other salinity and other radioactive isotopes and whatnot. And the current notion is that, oh yeah, the ocean is just a two-layer thing. And it's just whatever is diffusing is coming from the top kind of thing. But then when we look at these profiles of temperature and salinity and all of these other things going on, those things don't really square, right? And so it's from this, it's a nice read, this paper. I would recommend it to go over it if you haven't. But what he concludes basically is well, there must be some sort of upwelling happening, because otherwise there's no way that we have this the way the ocean actually looks does not match with our theories. And so, but if we introduce a vertical velocity in here, it gets better, right? And he mentions breaking internal waves as one of the driving forces behind this. And that is something that we'll come back to a lot in this course. Munk is also the person behind the Garrett-Munk spectra, which is something that will also come back in a few lectures. So I'm just planting that little seed for you to think about later. And then, yeah, take the past 5-6 decades or so. Theory has evolved a lot. We think about microstructure in a whole different light now. We think about spectra, and that's a foundation for a lot of this science as well. We have been able to describe spatial and temporal patterns of enhanced mixing in the ocean. We've done huge breakthroughs on parametrizations. That is, if we can't measure something in particular, we can measure a substitute for it, and that's the way we parameterize something that's easier to measure. We call that a parametrization. And yeah, we've done all of this work on mixing and how important it is for climate and ecosystems, et cetera, et cetera. Again, more in the lecture notes if you're interested. This is just a couple of interesting touch points. Let's see. Right. How about, that was some theory thinking. What about measuring turbulence? Well, that is hard. That's difficult, which is part of why we're here too. There is a lovely review paper by Michael Gregg on the study of mixing in the ocean and just covering a couple of touch points of that. Mixing, like actually trying to sample mixing, had a huge revival after the Second World War, where people thought that maybe there's a way to measure or like find traces of submarines. So like when you have a submarine going through the water, they would leave a wake, and what if we can like find that turbulence, and then we can see where the submarine was, right? This is Cold War era kind of. So this is a huge effort, a lot of O&R money put into this, Office of Naval Research, Navy money. It started with very basic temperature measurements. And that's the measuring of temperature is something that, you know, to study mixing is something that we'll come back to as well. Like technology evolved to be able to measure turbulence or temperature in centimeter scales. And they're also using something called a hot film anemometer. So you have a thin sheet metal, you put current through it, so you heat it up, and then you measure how much it cools off, can allow you to infer the velocity of the water that flew over that piece of metal. It's called a hot film anemometer. There's cold film anemometers as well, similar thing, depends on where you are. But yeah, and these are some of the very first of those instruments. So take a mental snapshot of this picture, this kind of instrument here, and then you'll get to see on the course next week how far we have come since then. Everything is getting smaller and slimmer and tinier, and it's cool. But yeah, this is it's an interesting read if you're interested in the evolution of instrumentation in particular. Where we are today, well, there's been a lot of technological advances. We can now measure turbulence in the ocean cheaper. Instruments have gotten more durable. And we have a better spatial and temporal coverage. However, measuring turbulence is still very labor intensive. It's very expensive. And so there's been a ton of effort, a lot driven by, a bunch of the people you'll hear about or learn from in this course, to develop methods for more autonomous sampling, and developing more durable sensors that can be put on things such as Argo floats, or like make it easier for ships of opportunity to do sampling, etc., etc. This figure here is from a paper by Jen McKinnon, who we'll meet next week, maybe, or the week after. And you can see that, you know, that top left globe there is kind of sparse. Like we're not doing a great job. Those are full depth log K profiles. And sure, this is from almost a decade ago, but it hasn't been filled in that much since then. So yeah, there's a lot left to do, and you know, this turbulent dipycnal fluxes are moving into becoming one of these essential ocean variables with like effort and manpower behind it to actually sample it to a degree where it's like useful for science. So yeah, again, I hope that was not just me a bunch of name dropping, but actually like the goal there was just to sprinkle a couple of seeds for you, so that when you hear certain names or words or thoughts or concepts, that maybe, you know, it's like, oh yeah, it will come back during or over the next few weeks, just so you know. Okay, deep breaths, and then we're going to go into reviewing a few useful concepts, like fundamental concepts for turbulence. I have here on the slides diffusion, mixing, stirring, and turbulence, and let's work our way through these. So we'll begin with diffusion. Imagine I have a beaker of water, and then I add a little bit of sunlight, and the top layer, oh my goodness, just slide some away. I should not step on this thing, I think that's a problem. We add a little bit of sunlight, and the top layer gets warmed up, so it's heated, and now suddenly we have a gradient of temperature in this beaker of water, right? And what is actually happening on a molecular level, these are little Mickey Mouse water molecules, and what's happening is that the surface layer has more energy, more heat, right? And due to Brownian motion and like these uppermost water molecules they start moving more, and then they push on the molecules that are below them, and then sort of like transferring their energy down, right? Seems fairly familiar. This is what we call diffusion, right? Diffusion, we typically talk about scalar diffusion, right? A quantity with a magnitude, but no direction. Think of a chemical, a temperature, the like heat, salt, something like that. Diffusion happens from high magnitude to low magnitude, and it's due to this Brownian motion, the random walk of molecules, right? We can talk about steady state diffusion, which is diffusion in time. We think of a flux, right? We have some sort of steady gradient, and this formula here, J, gives us just like how much of that scalar amount of that passes through a certain area per time. We have a diffusion coefficient D, which depends on both the thing we're trying to diffuse, so the scalar in question, but also the medium through which we are trying to diffuse the scalar, right? So like, let's say gas through some sort of like regular air is one thing. I don't know, salt through honey would have a different sort of diffusion coefficient compared to salt through water, for example. Then we also have Fick's second law, right? And this is now thinking about how the scalar changes over time. We still have a diffusion coefficient there, and but now we moved into using the Laplacian of the scalar quantity. So it's like 3-dimension, and not just 2. Or sorry, I should say second order instead of first order. And this is what we call Fickian diffusion, right? Fickian diffusion is diffusion that follows Fick's second law. It's down gradient from high to low magnitude and can be described by a second order differential equation. Again, sprinkling some seeds. We will come back to some of these things later in the course. When we talk about diffusion, we talk about molecular diffusivity versus eddy diffusivity. So that D I was talking about in the previous slide is, a coefficient that tells you something about how easy it is to move this scalar, whatever it is, through a medium in particular, right? Molecular diffusivity is through molecular collisions only. It is typically very small, microscopic motions, and it depends on particle properties primarily. Then we often talk about eddy diffusivity, which we describe with kappa instead, where kappa is a lot bigger, macroscopic, talking about centimeters to kilometers, and it depends on flow properties. So it's like we have the molecular collisions being enhanced by turbulent motions. So molecular diffusivity, slow, eddy diffusivity is kappa. And this is some of those things that Walter Munk was talking about, where he was like, molecular diffusivity is not enough to explain like what we're actually seeing in the ocean. There must be some motion happening here, the turbulence, right? Which is why we bring in the kappa, which is the molecular stuff enhanced by turbulent, flowy motion things. Questions on that so far? Yes, Tommy.
For the slide above, with the second law.
Yeah.
And determining the steady state versus the second law. So is that more of a turbulence state that we use that equation?
So it's basically just what question you're asking. Are you looking for the flux, which is Fick's first law, or steady state diffusion, or are you looking for how the scalar quantity changes over time, which is Fick's second law? Yeah, good question. All right. From diffusivity, we are moving on to mixing. So I have my beaker again, in which I have this gradient of some sort of quantity. Here, heat. This is what was warmed up by the sun a little bit before. And if I leave this for long enough with sunlight being input, we're going to have that, like all of that molecular diffusion is just gonna seep through, right? The heat is gonna go from top to bottom, and eventually we're gonna end up with something that is homogeneous, right? The gradient has been erased out, and this is basically mixing, right? Now, note that there's a difference between mixing and mixed, right? This beaker on the right is completely mixed, right? But the process of mixing itself is the irreversible process where a gradient or like water masses of different properties actually homogenize and they end up with the same thing. And these things are thus like across isopycnal, right? We move through some sort of gradients or whatever it is, and we end up with something that is homogenized. The process is called mixing, and then we end up with something that is fully mixed. Now, if you've ever taken a lecture by the wonderful Peter Fangs, one of his pet peeves that he will tell you is that we call it the mixed layer, but technically we maybe should be calling it the mixing layer, right? That there's a distinct difference between these two, mixing as an active process, mixed as the final result kind of thing. For this class in particular, one of the important things to take away here again is that mixing is an active process. It involves a homogenization of gradients and smoothing out of whatever it was. And yeah, but be mindful of like mixing versus mixed. Yeah. Seems fair? Cool. Next up. Sorry, was that a question? No.
No.
I
So
love
in
questions.
the ocean, like, do you ever really get to mixed state? Like you said, like in this case scenario, this makes sense, but in the ocean,
Yeah.
how do you define that then?
Yeah, exactly. That's a good question. And this is then like, you know, we can get a bit sloppy with our terminology sometimes. We talk about like turbulent, we talk mixing, and you know, it's like what you actually mean exactly when you say things, and you can have things that are on like some scales. If you zoom in, it can be perfectly mixed, and then you zoom out a little bit and you talk about it as like, oh, but it's mixed. But it's like, then it's not. So there's a question of scale too when you look at things. But yeah, it is, I would say in the ocean, kind of rare that you achieve like perfect mixed, like over any sort of larger set of volume that you're like, have smooth out every gradient perfectly kind of thing. Especially because in the ocean, it also matters which scalar in particular you're talking about, right? Salt is one, temperature is one, some sort of other chemical is one, so you can be mixed in some ways, but not mixed in other ways. Does that make sense?
Yeah.
Yeah. All right. Next up, stirring. Stirring is the physical process by which we stretch and fold water masses through currents, eddies, waves, etc. And we move things around, which is good because we are good. I'm not going to put judgment on this, but what we do when we do that is that we stretch out or increase the interface between water masses of different properties, which increases the area over which things can diffuse, over which that molecular diffusion can happen. And yes, I have drawn arrows in both directions here, and that is because I want to illustrate that you could have different scalars going in different directions. You could have temperature going one way, salinity going the other way. You could have something, oxygen or a dye or whatever you have going in opposite directions. Double diffusion. We'll come back to this later, but yeah. The typical picture you use to illustrate this is little coffee and cream, right? Just a picture, pretty thing. And yeah, remember, stirring is a long isopycnal process, and what we do is that we increase the area over which that diffusion can happen, so that we can get towards something more like a mixed, final, homogenized thing. Now, why do I say that? It's because stirring doesn't always involve mixing. Cue YouTube video. Okay. Oh my gosh, sorry. That was very loud. gonna take that out. Okay, so this device is a round jar that can spin, and it's filled with corn syrup. And what they do is that they put in some dye of different colors in here. It's new scientists, it's very fancy. And it's also very elaborate, they do everything. But what he's doing now is like, you see that dye, those are lumps, and now we start spinning, right? This is the stirring bit, where we're churning things around, imagining this is like, you know, some water going over some topography, maybe, stirring some things, right? Seamount or whatever, and they're doing this very carefully, spinning around a couple of laps here. And then, right there, he turns around and starts going the opposite direction. What do you think is gonna happen?
It's gonna end like it started.
It's gonna end like it started. Yeah? Let's see. Drum roll, it's another couple of seconds on the video, awkward pause. There's a little ad there as well, and apologies for that one. I'm gonna hit pause at an opportune moment, like that maybe, or just like a tiny second more. Look at that. Ignore the ads, but we are roughly back to where we started, right? So this is a prime example of stirring. We stretch and fold things, right? But then we could reverse it back to where we started. So this wasn't a long isopycnal thing that we could revert in the ocean, would have been, but yeah, we could reverse it back to where we started. So there was not really any actual mixing taking place here. The dyes didn't just like diffuse and turn this corn syrup into a homogeneous, lightly colored, I don't know what happens when you mix blue, yellow, and red, maybe a brownish, I don't know. It's not one homogeneous colors. These blobs are actually back to where they were. So there was no across isopycnal like actual mixing. This was just stirring. So that's another thing to keep in mind. Stirring can happen separately from mixing. Yes?
Can stirring occur across isopycnals?
The definition of stirring is that it is like a long isopycnal.
Oh, but not across isopycnals.
No, so that when you go across isopycnal, you're in like diffusion, things that are mixing kind of thing. And the stirring bit is just like you're stretching and folding things, increasing the opportunities for mixing, diffusion to happen. But yeah, dye moves the D, the molecular diffusion for dye is like so, through corn syrup, is like super, super long. If you left this for, I don't know, many years, maybe everything would have sort of diffused and homogenized into one color. But at like, in the timescales we're looking at here, those blobs are kind of go back to normal. Yeah, Kaylee.
How do you define mixing in this particular example when, I guess except for the dye versus the corn syrup, there is no, like, I guess the isopycnal distinction makes sense to me in the context of water with different densities, but how do you talk about it here?
So here it's more like, yeah, again, think about it in terms of diffusion here maybe then, like if you left this for long enough, this dye would actually start to seep into the corn syrup. Right now, that is like these blobs are like, it's a little pocket of dye right now, right? So if you want to think about it in isopycnal kind of term, imagine it then being like the dye pocket crossing into the corn syrup structure kind of thing, which again is not happening on any of the own time scale we're looking at here because it's too slow. Does that make sense? Does that help?
Yeah, I think maybe my question is, it seems like if this is an example of the difference between stirring and mixing, I wonder if there's like a more fundamental way to define stirring and mixing, which doesn't use the word isopycnal.
Isopycnal, sure, yeah, I mean, again, mixing is when you have homogenized something. Stirring is when you just have stretched two fluids of different properties. You've increased the surface area between them, but you haven't necessarily actually blended them. Does that make sense? Is that better? Yeah, we'll come back to that one in a minute. Yes.
So stirring can happen in the same layer that if you break the isopycnals, you have mixing.
If you have breaking, yes, then you start moving into like diffusion and things going to happen. And this is like very textbook example of like isolating one process and separately, like in the ocean it's very rare that you see like, oh yeah, this is exactly this or exactly that, yet you're gonna have everything happening at the same time kind of thing, yeah. Eric.
So just making sure that I'm using the terms correctly, stirring increases the surface area, allowing for more chances for diffusion, and once diffusion occurs, that's considered mixing.
Yeah.
Okay.
What he said. Yes. Perfect. All right, good. I like this. Okay. Turbulence, last one on the list. So we're back to our beaker with a gradient, right? And then what do? I'm very proud. I made this animation or this little graphics. I'm very proud of this one. What do? We shake it. And when we shake it, what we do is that we add like chaotic fluid motion on multiple scales from like the tiniest stuff to the bigger like whole beaker shaking. And what we do then is that we like, it's basically like we're similar thing but in a slightly different way where like we're increasing the opportunities for that mixing to happen, for that diffusion to take place by like adding a bunch of mechanical energy. In the ocean in particular, some of that mechanical energy is typically used to overcome buoyancy gradients, like stratification, right? Lighter fluid above heavier. When you add a bunch of like shaking, mixing, whatever, turbulence you want to call it. See, there I used mixing in the wrong sense. I should have said turbulence. When you add a bunch of turbulence, what you give is that mechanical energy that then allows for better mixing, more diffusion to take place, more chance for these gradients to be homogenized or evened out. All right, there. I'm gonna put them all on one slide for y'all again, just so we can go over them, and there are verbal definitions of all of these things too in the lecture notes for you. So, diffusion, that was the molecular spreading across trying to even out gradients. Mixing is when we have irreversibly blended things across isopycnol. Think about the mixing versus the mixed. Stirring is when we rearranged water parcels along isopycnals, so we increase the surface area for diffusion to take place. And turbulence was when we added a bunch of chaotic mechanical energy motion that can boost mixing. All right, see some of you are taking notes. I'm gonna give it 30 seconds for this to just sink in, some notes to be jotted down, and then I'm gonna show you a cool video on the next slide. Okay, actually I have no idea how long 30 seconds are, so I'm just gonna go ahead and show you the next slide. Okay, maybe you have seen this, maybe you have not. This is a video from NASA, where they have taken a bunch of ignore it's not speaking, we don't have sound on, but they've done altimetry and they just looked at the surface of the ocean and currents. And this is, in my opinion, this is gorgeous. This is like, it's very pretty. You see the full globe coming in on the Gulf Stream right there. You see all of those little swirls that come out of it. You have a bunch of water moving here along the equator. It's a little bit more silent in other parts of the ocean. But yeah, we come in on the Kuroshio spinning around, and it's just very pretty. And maybe I can skip forward in the video a little bit to show you some. To show you, oh yeah, here we go, here's the Kuroshio. Why am I showing you this video? Well, basically, everything here is turbulence, right? Like this is the stirring, this is the chaotic, like, the things being shaken up, mechanical energy and putting stirring from the things, diffusion happening, right? Like, when we think about turbulence or ocean mixing, we think about like, oh yeah, this is like a small scale thing, right? Like this is like centimeter scale, and it's like that, you know, we're trying to measure the fine scale microstructure, right? But if you zoom out and you look at the whole planet, we're basically looking at the same things, but at just a different scale. Does that make sense? Yeah? I don't know, I just like this video too, it's pretty. So, we don't have to watch the whole thing, but yeah, you can search for it online and you can watch the whole section if you want, it's very cool. to see eddies being spun up from the Hierogulus current, etc. Okay. Next slide. Here's another question for y'all. Why do things move?
Because Earth is moving,
Sorry, because
and Earth is moving.
the Earth is moving, yes, and the Earth is moving. We're all just monkeys on a flying rock through space, if you think about it. But yes, things move because the Earth is moving. And what that does is that it introduces forces, right? And so, I hope you remember Newton's second law, it's one of my favorites, saying basically that how something moves depends on like some of the forces on all of the forces on that thing, on that object, right? So, what are some forces that a parcel of water might experience?
Gravity.
Gravity, like that one, yes. Gravity in the vertical, up and down. We're all bogged down by gravity on a daily basis. Yeah, Eric?
Buoyancy forces or temperature differences.
Yeah, exactly. So similar, it's like, something is heavier, lighter, gravity is different on it, it is moving around. Yeah.
Wind.
Wind, yeah, some sort of like pushing, like a stress that is sort of like shoving things to move. Yeah. Anything else? No? Inertia, yeah. Austin, I saw your hand.
Coriolis.
Oh, it's my favorite. Yes, that one. Cool. Nice, you got a bunch of them. Where I'm going with this, obviously, is the Navier-Stokes equations. And this is the part that's going to be a lot of equations on the board, on the slides. Apologies in advance. It's all in the lecture notes if you don't want to write it down. I assume that you have seen this probably at some point. Maybe it was earlier in your grad school career. But yeah, let's just go through it, and then this is more of a like fresh refresher to make sure that we have seen these recently, because they will come back in a bunch of the stuff that we'll talk about later in this course. So, yes, from F equals ma, we go to try to pick out that like the A part and try to list all of our forces, right? So A is the same as du to t, right? I have assumed that the flow is incompressible, meaning that density doesn't change significantly with pressure, like a gas. Water is, we say that it's incompressible. So that way I have done away with the m, and I can just roll with density rho instead here. So, what are some of the forces we have? Advection, I forgot who said that, but yes. We have the Coriolis force, right? And note that that only acts not in the vertical, but only in the horizontal. Chuck those on that side. On the other side, pressure. Viscous forces, some of those stress terms that you were talking about, Tommy. And then gravity. And in the Navier-Stokes equation, note that we're actually thinking about gravity as the effective gravity. I don't know if this is a familiar thing for some people. Effective gravity is the vector sum of the true gravitational acceleration from just like us being on Earth and the Earth pulling us down, and the centrifugal acceleration, which is from the Earth spinning. And the centrifugal acceleration on the equator, these two are in the same direction. As you move higher or like at a different latitude, these are going to be in different directions. So that is, for example, why when I did physics, someone asked me what's G, I would say 9.82. What did you guys learn that G was? 9.81,
9.81,
yeah. Anyone go to school here? Like 9.7 something, right? No? 9.7, whatever. I see a few nods here and there. Yeah?
I still have 10 months.
You still have 10 months? There you go. Yeah. No, but just, yeah. So if you ever wondered why people can't agree on G, it's because you think about it at different latitudes. For most intents and purposes, it's fine. But yeah, technically there's a latitudinal aspect to this, yeah. Effective gravity, right? The pull of the Earth and the resulting like spinning act. Okay, and then what we do too is that we often take the first two terms, and we put them together in what we call the material derivative. This is probably the most common way that you have seen the Navier-Stokes equations. And this way of writing it captures the Eulerian and the Lagrangian perspective in one. What do I mean by that? Eulerian, it's like we're standing still, we're just watching. That's the first bit, that the dV/dt. We're just standing, watching, see what comes by, right? And then the Lagrangian perspective, which is us moving the flow, seeing what's happened. So we put those together, call it material derivative. Sometimes it's written out, sometimes it's not, just to remember so that you have it. And then yeah, if we sum all of those things, that's the top view there, and then I've split it into the x, y, and z direction. Again, like I said, the Coriolis only happens in the x and y directions, and then gravity only happens in the z direction. To this set of equations, we often add what we call continuity or conservation of mass, which is basically saying that, take the gradient of like the x, the u, the v, and the w, and that should all equal 0, meaning that like what goes in comes out, right? Like we're not magically, transforming something into something else, water to wine or whatever, larvae into butterfly or whatever. But yeah, continuity, what comes in, what goes out. So this set of the Navier-Stokes equations in the different directions and continuity is typically like how we start a lot of our derivations of a bunch of the equations that's going to come later in the class. Now, what's cool about this is when we break it up and we think about these different forces that act on water parcel, we can start thinking about balances, right? The whole name of the game is to try to simplify the situation we're looking at down into as simple as possible of an equation for us, which is why we often talk about these common force balances or concepts for various things. So I'm sure you have seen some of these, right? We talk about geostrophy, where pressure and Coriolis balance, right? Yes, no, geostrophy is familiar, yeah. Hydrostatic balance, that's in the vertical, where we balance pressure and gravity. Thermal wind is also a form of balance in some ways. We think about geostrophy and hydrostatics basically balancing. When we compute the Ekman velocity, that's us balancing Coriolis and vertical turbulence stresses, right? Yeah, so again, the name of the game is to try to figure out what is important, what is not important, and then we simplify the situation we're looking at down as much as possible to get ourselves to some sort of balance. But again, these are also some of the assumptions that Andrea talked about earlier, that there's a lot of assumptions that goes into turbulence in general. So yeah, just a refresher on what these things are. And then how do we know which force things are important? To help us with that, we have a bunch of these non-dimensional numbers, which I, for the life of me, can never remember. I need to have several post-it stickers around my desk at all times to remember these. So if some of these are not stuck in your brain, that's totally fine. If they are, good for you. Please tell me your secret. But yes, we'll go over them, a couple of them here, and they're also in a convenient little table at the end of the lecture notes for you to refer to if you need to. Okay, first up, the Rossby number. So the Rossby number, we compare Coriolis forces, or Coriolis, with effective inertial. U over FL, U is a typical velocity scale, and L is a typical length scale. And the question we're trying to answer here for the Rossby number is basically, does rotation matter? If this is very, very small, that means that the denominator was a big number, which means that rotation is probably important. And if it's a big number instead, we can say that the F part was probably, like F and L, like the scales combined, were probably, not much, and that this rotation doesn't really matter, so we can take that out, take out the Coriolis force from our brain, thinking about this. Next up, we have the Reynolds number. which is something we'll come back to in a lecture from Helen a little bit later. In this number, we're thinking about the viscous versus the effective forces, right? So again, typical length scales. New at the bottom is something Helen will go over a bit more too, but what we can do with the Reynolds number is basically ask ourselves the question, is the flow turbulent or laminar, aka does viscosity matter or not? And again, planting a little seed for Helen to pick up on later. Richardson number, which you might have heard of as well. The Richardson number is thinking about buoyancy, which you can say is basically gravity, versus shear. So shear, vertical shear is how velocity changes with depth, UDC, dVdc, etc. M squared over shear squared, S squared. And this is basically asking, will stratification suppress turbulence? Because that's another thing, right? If you have stratification, so if you have like light things above heavy, when you start shaking that thing, like adding mechanical like turbulence to it, you have to fight the buoyancy gradient. You have to take something that is heavy at the bottom, and you need to give it enough potential, like enough kinetic energy to move so that the potential energy, like you put heavy above light, right? Like, which is counterintuitive, and that costs you energy. So in some ways, a fluid that is perfectly mixed, that is like no gradients at all, if you shake that, you're gonna have more turbulence. Like you don't have to give away any of your turbulence to overcome stratification, that energy. Does that make sense? Yeah? Yeah? So again, just like a couple of these concepts, turbulence versus mixing versus mixed kind of thing. But yeah, Richardson number is something we'll come back to as well.
Wait, sorry, what is N?
N is stratification. So it's a buoyancy frequency. Yes. I should have written that out too. That was my bad, sorry. And last one is Froude number, which I honestly think I've never used. Maybe I should at some point, but I've never used it. But this is thinking about buoyancy versus effective forces. And this is still like a similar ties into stratification, and whether or not the how layered whatever water we're looking at is, and whether or not that is of importance. All right. I have a summary slide for y'all. So, what I hope that you take away from me talking for the past hour, we did a couple of touch points into turbulence theory and turbulence sampling over the past 100 to 150 years, right? There's a lot that has happened. We have learned a lot more about the ocean, and you are lucky enough to be in a class where you're going to meet some of the people who are doing some of the cutting edge research on like instrument development and theory development for turbulence science. So that's cool. And yeah, we've done a lot over the past 100 years. All of the names I talked about today will probably come back in one way or another over the next few days. And we have also started to realize that mixing is of importance, not just because it's cool or we think we can see traces of submarines, but actually because it is of importance for waves, energy, climate modeling, ecosystems, nutrient fluxes, carbon cycles, and more. And yeah, then I have my 4 little graphics at the bottom there again, just to refresh your mind. All right. We have about 5 minutes left, which I was hoping to, if there's anyone who has any questions so far. I can check on Zoom, there's no one in the chat. Seems fine. Any thoughts, anything? It's like, if you don't want to ask right now in front of everyone, then we can also just go to break and you can stretch your legs and grab a snack in the back, and I will be right here if anyone has any questions. All right, yes, Eric.
Just a quick question.
Yeah.
You mentioned having turbulence in a homogeneous fluid, I guess. So in that case, would the turbulence just be movement and there would be
Yeah.
mixing.
Exactly. The turbulence then, if you have something that's perfectly mixed and you shake it, you technically have a bunch of turbulence because you have a bunch of like chaotic fluid motion, but there's no mixing happening because everything was already mixed beforehand, and you're just shuffling things around. Yeah. Good point. Cool. Okay, I will be right here. Y'all go get a snack, and then next lecture is 30 minutes from now at 11 with Kite lecture. Cool.
Thank you.
Thank you, guys.
Can I?
Yeah, please chat to me.
Um,
Yeah, I'm here.
Just clarifying. So the difference between mixing and stirring,
Yeah.
I really like the experiment that you put there.
Yeah.
And it's like this reversible versus irreversible process. And
Yeah.
so with it, just to make sure I understand things, mixing basically cross-isopycnol